good afternoon. So our presentation is titled Non-Intrusive Plant Dynamic Monitoring using mmWave radar. Firstly, I would like to start about giving a little bit of background how we got into this research. So this research is a collaboration with also two KU Leuven research institutes. So we are mainly working on electronics, but we are working together with the Leuven Plant Institute, and they are doing research on controlled environment, agricultural and vertical farming. And so what they need, or what they are really interested in, is how can we automatically sense how our plants are growing, and can we detect early anomalies to prevent this and optimize growth. So they really need this real-time plant level feedback. Currently, there are a lot of solutions on the market, which can mainly be categorized in two categories. Firstly, we have some intrusive methods. So you can have some wired probes or contact sensors that are mounted on the plants. These are very nice. So, for example, you can do IMU-based detection. But the big issue here is that they are intrusive. So for some plants, they are just too heavy to actually measure. And that is why there are also some non-intrusive methods, which have a big advantage over them. Most of them currently are camera-based. Here also there are some issues because of lighting and occlusion. You might have some challenges detecting certain patterns when it gets dark, when the lighting changes. It can get a little bit more difficult. And we were doing research on mmWave radar at the time. So we started wondering, maybe we can also use this in this use case to detect in a non-intrusive way what plants are doing. So this is a bit of the motivation behind the work. I would also like to explain very shortly what the principle of FMCW radar is, because we will use this later in our sensing solution. So FMCW radar stands for frequency modulated continuous wave radar. Most people are familiar with radar, I guess, but it's basically your radar transmits a signal to your target. The target reflects the signal back, and the radar is going to receive this reflected signal. And based on the time of flight between the target and your radar, you can calculate the distance. In the case of FMCW radar, the signal that will be transmitted is a chirp signal. So this is a signal of which the frequency is linearly increasing over time. This has numerous advantages, and in this case of radar, we can actually simultaneously measure both distance and velocity. So this is over time what our signal looks like. The blue signal is our transmitting signal. It's linearly increasing over time in frequency. And this is determined, the rate at which it increases is determined by the chirp rate, the sweep rate, or the frequency slope of our chirp. And what we see is that the reflected signal, the frequency difference at which we reflect the signal, is scaled to fixed delta t, which also corresponds to, so our time delay is proportional to the distance of our target. This is proportional to a frequency difference of our two signals, and this will directly allow for a distance measurement. So the slope rate of our chirp signal, this is something that we can choose with our sensor. The time of flight between our target and our radar is 2 times the distance, because the signal needs to travel back and forth, divided by the time of by the speed of light. And so we can directly measure a distance from our frequency difference between these two signals. And this is what we can actually measure at our radar signal. This is can be executed in hardware, so this is easily possible. And if we even have multiple targets, we can do frequency analysis to get back the components from multiple targets. So this is a bit about the background of radar. What did we try with this? This is one of our office plants that we have on the right-hand side. This is a Calathea plant. And the Calathea plant has a very day-night cycle that varies a lot. Like in the day, the plants are sucking down a bit, and during night, the leaves go up. And what we wanted to try is, can we actually track this with millimeter wave radar? So this is our very simple setup. We have our Calathea plant, and we have Texas Instruments IWR 6843 radar. So this is a commercially available radar module that is mounted rightly above the plant, and it is pointing directly at one of the leaves. And our module is connected with a Raspberry Pi to do the data processing and logging. So very simply, our Raspberry Pi sends the configuration of our chirp parameters to the radar module. The radar module will transmit a signal. It will reflect on the plant leaves. The signal will be received by the radar module, and then we can log the range profile of the plant. And this is what we have done over several days. So a little bit more about the settings. The radar module is a 60 gigahertz radar module, which means that we can use 4 gigahertz of bandwidth. In theory, this means that we can get the resolution down to 3.75 centimeters. In practice, there are some limitations. This means the range resolution is a slightly bit more coarse. And we get a range resolution of 4.36 centimeters. So we wanted to see if this is actually enough to accurately track the leaf moving. So, for example, if we do one singular measurement of our plant, this is what we get. So here we can clearly see some peaks that are corresponding to the plant leaves. And here there's also some noise from the mixer. Here, nothing is present, so this is like 20 dB lower, and we can clearly see the peaks of the signal reflecting on our plant leaf. So this is from a singular measurement. What we did is actually track this over 2 weeks. And what we can see is that every day we can clearly see the plant moving up and down because of the day-night rhythm. So during daytime, the leaves go downward. During nighttime, the leaves go up. There's also some more interesting things we can see. Over the first few days, the plant has slightly grown, which you can see by a steady incline of the signal. And we can also see some slight variations when we water the plant more or less, but this is difficult to see in this figure. So what we do is from this peak, from the last figure, we can actually calculate the centroid where the leaf is present, and this is the black line that we see over time. So to conclude, we were looking at the potential of millimeter wave radar to see if we can use this non-intrusively to monitor a plant. And I think in this we were very successful. The circadian rhythm of the plant was clearly visible in a non-intrusive way, and also its advantage over camera-based systems that is very lighting independent. So during nighttime, it also works perfectly. Future work will include also expanding this towards larger arrays for greenhouse applications. And also what we would like to do is also look at the amplitudes and relative amplitudes of the signal and see if we can link this towards water level contents of the plant leaves. That's it. So I'm very happy to take any questions.